Welcome everyone to day 2 of the 4th annual UK conference. Thank you again for joining us. Yesterday was a fantastic day. We had some great conversations, especially in the afternoon. Very heated topic, I would say, and a very important one too. So thank you for all your comments. Thank you for everyone that's online that's also been chatting with us. So wish it was a little bit more one-on-one, but I guess sometimes you just got to be here. So with that, Mark Wilkinson will help start off the day. Mark?
Great, thanks Brian. So welcome everyone to day 2. Thank you all for turning up. I'm impressed that you're all here at 9, though most of you haven't had to travel very far to get here. I hope you all enjoyed the dinner, those of you who were at the dinner last night, and I would like to thank WECA, DDN, Q Associates and NVIDIA for very kindly covering the costs of the dinner. So that was, maybe give them a round of applause just to say thank you, that was appreciated. So I'm abusing the first slot of the day to just say a few things. I'll try to keep it brief, and Brian will make sure I stop on time. So I just wanted to say a few comments. Quite a few of these points have been made in various ways in the discussion yesterday, because I thought yesterday was the talks were great, and I think the discussion we had around the talks was very, very good. So I'll just give a different take on some of the points, I think. So the point I want to emphasize, and this came across in various contexts yesterday, is that as probably all of you think of it in these terms, but high performance computers are not just computers for us, they're scientific instruments. And the reason I emphasize that is, in terms of how we design scientific instruments, we need to think about what it is we're trying to do. And that came up in lots of talks, that we really need to focus on what it is we're trying to achieve with computing. We're not just buying computing because it's there or because we have funding. It's because there are scientific things we want to do with it. And that should feed into how we think about what systems we need and how we then actually design them. Now, there's many reasons why computational requirements are increasing. It's often because of increased resolution or increased complexity, so adding more physically realistic things to the models, or a combination of the two. Sometimes it's meaningless to go to higher resolution if you don't add in extra processes. There's a lot more coupling of models on different time scales and length scales, and an increasingly important aspect is uncertainty quantification, so that simulations or AI models or whatever are actionable, so that we actually get information, not just an answer, but uncertainties on that answer, so that we can use it. We heard yesterday about how AI and simulations are converging in many ways. The point I would emphasize is even the workflows are converging now. In the simulation community, we're seeing a lot more use of AI within the simulations themselves, either for analyzing the output, that's the more traditional way for looking at the output and comparing it to experiments or observations, but also within the simulations itself, replacing subgrid physics or sub-resolution models with AI-driven models, surrogate models instead. And obviously in many fields with experiments or observations, you have to actually have large-scale compute associated with the telescope or the experiment. So that, a good example of that is the SKA that Jeremy Yates talked about yesterday. So that we're actually, there's AI, large-scale compute, and using AI in order to just handle the data as it comes in. And so that means we need a whole ecosystem of different types of compute on different scales. So one example that came up yesterday, why should the UK be funding large-scale compute? So there's many use cases. There's many use cases. I'll just pick on one. It was already mentioned yesterday, but I think it's a good one, and I'll say at the end again, we need to be making this case to government and to funders why it is what is the value of computing, so that it really is appreciated and not just seen as a thing that would be nice if we could afford it. So nuclear fusion, UK AEA have been tasked with delivering commercially viable fusion by the 2040s. And the timescales for doing traditional prototyping, where you build something, see if it works, if it works, that's good, and then you improve it, the timescale for that will mean the next one that they build after the one that's being built now has to be the commercially viable one. And that's not possible. So the only way you can do it is if a whole series of prototypes are done in silico. So we have to be able to simulate the whole, all the aspects of essentially building a digital twin of a nuclear fusion power plant in order to do that. So that's one example of a use case. As we said yesterday, that requires a lot of compute, but it also potentially delivers a net zero solution. But it's not just big problems like that. Many industries need to be using more compute, and particularly small companies. Large companies can often afford to have the teams of people that are needed to support HPC or take advantage of it, but SMEs often don't, and that's an area that I think we need to be much more engaged with as a community to make sure that everyone who could benefit from using HPC has access to it. So, as I said earlier, computers are scientific instruments. If you were building I'm an astronomer, so all my examples will be astronomy based. If you're building a telescope, with the greatest respect to the government, you wouldn't ask a government minister to design the telescope. You would just say, we think astronomy is important. To do astronomy, you need a telescope. So astronomers go away and design a telescope, and here's some money. And it's important because in astronomy, you wouldn't go to the astronomers and say, you SKA radio astronomers use telescopes, and you optical astronomers use telescopes. Why don't you just have one telescope and you both use it? Because they're doing totally different things at different wavelengths, and so you need different types of telescope to look at different types of problem, and it's the same with compute. So the process we go through in Dirac, which I hope will be a similar process, will be used for UKRI decision making, is we start from the science case. So again, that was emphasized in talks yesterday. We start from what do you want to do? Not how do you want to do it, but what is it you're trying to do from a science perspective. We get that peer reviewed. That gives us essentially our underlying business case for why we need funding. We then do an assessment of what that science, in order to deliver that science, what do the workflows look like? We then divide up those workflows that have things in common to work out what services we need, and that's our technical case, and we get that peer reviewed as well. And after that, we then work a lot with industry. Many of the people in this room have worked with us over the years to co-design the system so that we actually design the technical solution we need. And the result in the case of Dirac, so I'm the director of the Dirac facility, and we provide HPC for the theory community within STFC. And we've got 4 systems, and they're designed around different workflows, so they have different architectures. I'm not going to go through all the details on this, but just to point out, I don't know, is Andy here? He was saying the slides always just show the technical stuff and never mention the science. I would just emphasize each of the boxes has a science bullet point in it. So I just want to make a point about 2 of the systems in terms of how the co-design process succeeded. So the top right is the Edinburgh Tersa system, which Antonin talked about yesterday. So it's a GPU-based system. That system, because of the co-design process, by the time it was finished and technical commissioning was finished, the work that had been done by the RSEs and the technical team at Edinburgh and the technical team at Atos meant the system was twice as performant for the grid code as had been bid in the tender. So in the 6 months of work that went into getting everything set up and running, we'd actually double the performance of the system. So that was a real success there for Lattice QCD. And the memory intensive system, Cosma 8 in Durham, that Alistair talked about yesterday, that is, it's about 40-odd thousand cores, but it's being used by major European collaborations to do cosmology simulations in preference to PRACE systems with 4 times as many cores, because it's been designed for that cosmological workflows, and it actually is much more efficient for them. And much more efficient in this case actually means that you're using, it is more sustainable as well, because you're actually using less energy overall to do the simulation relative to what you would need on those other systems. So that's examples within the Dirac community, but the advantage we have is the community is small enough that you can kind of go through the process that I've described of identifying the workflows and grouping them. So the question then is, how do you do that on a UKRI scale? So there's already a science case. So we've got step 1 done for UKRI. So we finished that in 2020. There's also the red document was the Government Office for Science review from last year. From last year. It's actually very good. So lots of reviews are not worth reading. That one, I think, if you only want to read one review this year, I would say read that one. It was very good, and it's actually the basis for the DCMS review, the future of compute that's going on at the moment. So we have the kind of underlying case. So then, as I said, the next thing you do is once you've got your science case and you know what it is you want to do, you have to turn that into a technical case. And this is where software engineers come in. So I don't need to tell you how important software engineers are, but in case anybody doesn't know or anybody listening online doesn't know, that I wanted to emphasize this. So we need to have increases in compute to be able to compete internationally. If the UK wants to be a science superpower, we need to have the right compute that can keep us there. But we can't just get that from hardware, because we need software improvements as well. And you can't get away anymore. When I was doing my PhD, my code got faster just by waiting. So I never had to be very good at coding, because if I'd waited a year, it would already run faster just because everything was better. Now that's oversimplifying, because of course if you were really at the cutting edge of large-scale simulations, it's never been true that you could just wait. You always had to do more work. But we're now at the point where everybody needs to do more work. Especially if we want to move to more energy efficient hardware, it's generally harder to use. We heard about FPGAs being, I can't remember the phrase that we used, but let's say challenging. GPUs can be hard to program, and if you really want to get the performance, it does take a lot of effort, and software engineers therefore are vital for that. So within Dirac, we use software engineers for benchmarking, profiling, optimization, and porting. So that's all what you might expect. They've also played a key role in the procurement process. So in our most recent deployments, we were using the software engineers were involved in the procurement discussions, and the benchmarks we were using were all science benchmarks, not LinPack. We use LinPack just as a stress test at the end, but it's not one of our acceptance tests. And so the software engineers' input was absolutely key to the decision-making process, and I think that's a very important link to bring into the UKRI discussions as well. The other thing where software engineers are important is they can help to facilitate discussions between different communities. Because as I'll say in a moment, I think we need to get to a point where we're not talking about the STFC theory community, the FCIRC community, the MRC community. We're actually dividing things up by communities that have something in common. It doesn't need to be the science that they have in common. It should be their algorithms or the compute requirements. And RSEs are a really valuable asset in having those conversations, because they often know what's going on kind of under the hood of each field, and so that can be very important. So a few years ago, there was a set of community white papers. So this was 2019 when these came out. These were looking at all aspects of what the UKRI digital research infrastructure needed to look like. The title, can you hide that for a second? Because I've forgotten what the title is.
It's UKRI Supercomputing Ecosystem Principles.
Yeah, principles. Yeah, so this is the principles underlying the what the UKRI ecosystem should look like. The goal, which I think was echoed in several talks yesterday, is that we want to make sure that all UKRI researchers, and indeed all UK industry researchers, have access to the most appropriate hardware for the work that they need to do. And it needs to be enough of it needs to be the right type and the right scale of each kind. So in terms of how you get there, the scope and design, so these were the principles that were in the community white paper. It should be research driven, as I've already discussed. So you need a peer-reviewed science case, which we have, and it should be driven by communities of practice. So groups of researchers whose the thing they have in common is a workflow or a workflow type or a set of algorithms, and probably then you could they'd be able to use a similar type of architecture. The assessment should be based on scientific and industrial productivity. You need to do the economic return as well, but it's got to be that it has to be assessed. Success is defined in terms of what it is you wanted to do at the start. So if there are questions you wanted to answer, did it answer them? And sustainable funding, I don't need to go on about. Everyone here knows how difficult it is to have sustainable funding, power, staff, everything. In terms of delivery, again, community driven, so that we make sure it's targeting the right kind of hardware to support what people need. We need evidence-based decision making and co-design are two key inputs that we actually make sure we're getting the systems that we need and that we're making our procurement decisions based on real science benchmarks rather than things like LINPACK. And vitally, it has to be supported by investment in people and skills as well. And sorry, on the skills point, actually I'll say that on the next slide. So it's very widely understood how important it is to train more people. That's the title is Training People, the Skills Gap. Anyone who's trying to hire any DRI professionals at the moment knows how difficult it is. We've got a real shortage of people, and we've got really good people in the UK, and they're all moving around, and that's great. We just need more. We need more people. And so the e-infrastructure roadmap from UKRI highlighted that we need, if we're going to expand the amount of HPC and AI in the UK, we need the people to actually support that infrastructure. And another of the community white papers emphasized the need for training and the fact that whenever new infrastructure is built, we need to think, we need to think about the systems not just as the computer, but also the people around it. And again, that point was made yesterday. And it's encouraging that that's how DCMS seem to be talking about the infrastructure. They're talking about it as I think it's a techno-social infrastructure, so it includes both the hardware and the people, and that the two are absolutely both are required. I think in terms of attracting and retaining people within the UKRI side of things, we need to improve the career pathways for technical staff and software engineers. I think that's a real problem at the moment. And so the advantages and importance of training is that that's part of how the knowledge exchange happens. So one of the aspects of the DIRAC training program is we do innovation placements where we fund students or early career postdocs to go into industry, or in this case in the NHS, to work. And it's two ways, so they're learning skills from the community or the industry that they go into, but they're also bringing their expertise. So this is the first British Medical Journal paper to come out of this, so we're kind of excited about it because DIRAC doesn't normally publish, DIRAC researchers don't normally publish in the BMJ. The first two names there, Flavian Hardy and Johannes Heil, both did placements funded by DIRAC, and Maria and Jeremy are from the DIRAC management. And this was a study, it's just been accepted for the BMJ, and what they were doing was using machine learning to understand how good it's the English, and again, I need to, can you read me the title? Because I want to get the title of the hospital episode.
Data consistency in the English hospital episode statistics database.
Statistics, yeah. So there's a major data set called the hospital episodes statistics database, and it essentially just has records of everybody who's been in hospital, and it's being used more and more as more tools are developed to mine data like this. It's becoming a kind of reference data set. but it's incomplete. And so the question that this study looked at was using machine learning to understand how incomplete it is, where the problems are, and where the what the origin of the problems is. So what they did was they looked at three. The best thing to do is read the paper. I'm just giving you one of the conclusions. Three things: autism, dementia, and type 2 diabetes, and it was Parkinson's dementia specifically. And what they looked at was the reason for picking them is they're all conditions that once you have them, they tend not to go away. And it's also compulsory in NHS policy that every time you go to hospital, if you have one of these conditions, it should be noted in your record. So what they were looking here was how often in someone who had a diagnosis of one of these conditions, how often was the next time they went to hospital, was it missed? Was it misrecorded, or nothing was recorded, or something else was recorded because it had been mixed in with some other diagnosis? And so there's many different things that they concluded from the data. For example, in the case of autism, they found that there's a higher level of it being missed in women because of essentially preconception that autism rates are lower in women. Therefore, it's not something that's immediately thought of, and so or it's more easily forgotten when the person goes in. And so you can see trends. This is by the data the first time they were in hospital, and the chances, the percentage of subsequent visits that were missed, and you can see there are changes. So the dementia one, this is the number, so essentially the percentage here is how many times things were wrong. You can see they're quite high. They're 30 or 45% of the time it was missed in a subsequent case. But you can see in here, the overall trend for the dementia is that it's dropping slightly. So that could be encouraging. And again, they're looking at all of these trends need further work to really understand them. But you can see in the case of autism, it stayed very flat. So there's work to be done there. So in the last couple of minutes, I just want to say a little bit about Exascale. We'll be hearing a lot more about the Excalibur program in the next talk from Elizabeth. But in terms of how we kind of put all that I've been talking about together into an Exascale program, there's two activities that are underway at the moment. One is looking at an Exascale supercomputer around 2025, and there's other activities looking at accelerator-based pre-Exascale systems. There's various lessons that, let's say, I would draw from some of the big procurements that we've seen in the UK and internationally. I think co-design, as I said, is really important. It's very difficult now to expect, it's not really reasonable to expect the vendor community to do all the work of picking among all the various different configurations and work out what's best, because we know what it is we're trying to do. We need to work with them so we find out what the optimal solutions are. It's really important, as was said yesterday, that we're benchmarking against science use cases, so real codes rather than synthetic ones. And then there's a genuine discussion we need to have about what it is we're aiming towards. Do we want one exaflop system, or do we want an Exascale ecosystem, so a set of them? And so the title of this one is A Stepwise Path to an Exascale Ecosystem. So this is kind of one route that I would favor, and others of my colleagues as well. So rather than jumping straight from 20 petaflops, which is where we are now, up to an exaflop, instead have a series of systems, have different architectures in them, so there's some diversity, and we get experience of the different possibilities, and then work out what it is we need at the end. I think what we see in the supercomputing science case is within UKRI there's a huge amount of software engineering work still to be done, and Excalibur is doing a great job, but we're not ready. So there's a lot of work to be done. And from talking to industry partners, it's the same in industry, that again, there's work to be done, and that we need to start taking steps towards it first. There's There are some key benefits to doing this in a stepwise approach. It reduces the risk because it means we can actually deploy very novel hardware tested at scale before we go all the way to exascale. But we'd have large-scale production systems, and we'd have them sooner, so that we could, potentially have one next year. They also support community engagement, because it's clear that some communities, well, many communities, I think, there's no incentive to upgrade the codes for systems that might appear in a few years' time. You really want something because you can end your career very easily by just working on code optimization and not publishing anything if you're in academia. So it's really important to have something which you put in the effort now, you're preparing for the future, but you'll actually see a benefit tomorrow because you've got a system that you know you're targeting. So I think that there's a virtuous circle there where you start building the systems and then you start improving the codes faster, and then it kind of helps us to get momentum towards whatever system or systems we want at the end. And it also means the governance, because there's a lot of issues about these systems need to be shared across UKRI, so they won't be just for STFC or just for EPSRC or any of the individual research councils. We need new governance structures. We need, as was said yesterday in the context of cloud, we need to work out how do we do this, how do we allocate time when you're not going to be able to necessarily, it'll be very difficult to compare actual individual simulations from different communities and assess at that level of resolution that this simulation in astrophysics is better or worse than that simulation in engineering. So we need to have mechanisms that we make sure we're doing the right things with the systems. And the outcome I would favor very strongly is that we kind of take this stepwise approach, and what we end up with is probably an ecosystem where we've got several systems and they kind of grow over time. So you end up with however many exaflops we can afford, but in a set of targeted architectures, so that again we've grouped things by workflow type, and therefore the systems we get are more efficient. So my last slide is, second last slide, sorry. Just to say, one example of such a system is a project some of us are working on with Dell and Intel. So this is a system which will be based around the Intel Ponte Vecchio GPUs, roughly 120 petaflops. And again, this will be one of the precursor systems. So that's all the information I'm giving you in the talk about it. And you've got the snazzy logo. Paul Kaleja and I are here all day. If you'd like to hear more about it, come and talk to us, or send us an email. So the summary is, I think hardware and software co-design gives results in better systems in the end. And so I've stolen an equation from the Software Sustainability Institute, who said better software equals better research. So I said better systems plus better software equals better research. I think we really need to identify communities of practice so that we actually decide what services does UKRI need in order to cover all the areas within UKRI and for industry. Software engineers are really key in this. They're important in making the procurement decisions, improving our code, but also in terms of identifying these communities. And as I said, we really need to keep making the case for investment in HPC. It's not, I think we shouldn't take, there's a lot of positive noises in terms of the Go Science report and the DCMS report, but it's not a given that there'll be huge amounts of new funding. We really have to make the case very strongly. So yeah, so please all keep making that case, and yeah, I will leave it there. Thank you.